Good morning, ladies and gentlemen. My name is Jiří Navrátil. I come from CESNET, and I should chair this session, which is called Big Data, Big Deal. I would add probably the big problems also. And as you will see, there are also big guys. So we have had three talks. The first one is from Harold Teunissen. He is from SurfNet. He's leader of the middleware group, which is developing tools for integrating systems in the Holland. And the second speaker will be the Bill Johnson, who is the senior researcher for in US. He's currently working as advisor for the ESNet, is the network for Department of Energy. And the third one is the Stephen Pinfield, which is the senior lecturers from the University of Sheffield. So we have three speakers from three totally different areas. So you will have a chance to compare what they understanding under big data, big deal. Okay, so I will ask the first speaker, Harold.
Thank you very much. Yeah, welcome everybody this morning at the session Big Data, Big Deal, or Big Data, Big Deal. My name is Harold Teunissen, and I, as I said, work with SurfNet. My interest is all new things, which is of course big data, I think big data is the new cloud for this year. I'm not sure what the big data for next year is, but for this year it's going to be big data. Yeah, well, it actually started big data when I got my twins 5 years ago. And if you count up the number of pictures I got from these two, it's I think around 30,000 pictures. So probably all can relate to this, that everybody has its own somehow big data problem. How are you going to look through this data? How are you going to search through certain events? How are you going to store it? How are you going to share it? How are you going to process it? It's all individuals here that all have multiple devices around, doing stuff with music, movies, producing themselves, or at least looking or watching movies. But these two just changed my, say, big data perspective forever. Another thing is you got LinkedIn. This is my LinkedIn network. I'm somehow hooked up to that. And you can, there's a beta site from LinkedIn. You can make it a nice graph out of this. So does this really make sense to have such a network? Can I use these contacts here? Who are going to approach that? So you have a whole bunch of, well, you see, I had a couple of employees before, and you see that it's clustered around that, typically. But can I still perceive that sheer amount of contacts? This is a LinkedIn example, but it could also be a Facebook example or a Twitter or any other kind of social media or group you're a part of. But big data is of course not new. It's been around for a long time. And just an example from the 16th centuries, there was a whole industry around, typically in the Netherlands, which is pretty prosperous at that time, making maps. Collecting map data is, for that time, without GPS or any other means, with people on ships, with all kinds of diseases, getting all this data with a high quality on a map. It's very difficult. You cannot imagine how difficult that is. Even a bit closer. Everybody knows the new Hobbit movie. Peter Jackson decided to have a new frame format, I think 48 frames per second, 4K video. So it ended up with files of 8 petabyte. How are you going to deal with that in the production phase of your movie? Different scenes, different aspects, sharing the data among the different production facilities, but also looking in how you're going to edit this, different angles, communication with the post-production team. It's a whole mess. Just a bit about the organization I'm with. We were currently a big organization because we just brought all e-infrastructure or cyber infrastructure facilities under one umbrella in the Netherlands. We got SurfNet, where I belong to, is providing the high capacity network, of course, but also a lot of collaboration services. Since January 1st, we got the supercomputing and high performance computing on board. We do a lot with cloud services and the cloud licensing there. And of course, not to forget, we also have a collaboration with our Dutch National Science Foundation, I would call it, this NWO, in the Dutch eScience Center, where we try to help researchers to do their work with ICT means. Okay, getting back to big data. It's a hype, that's clear, as everybody understands that. So where we had cloud computing, it's for some that's the hype currently, but it depends on where you are in the innovation timeline. But now big data is pretty a hype. At this conference, big data is not really mentioned a lot. At least Stephen Wolf in his presentation or his talk this morning mentioned a little bit about it. We had a Birds of Feather session yesterday, but that's more or less it. And we believe that big data, whether it's a new term for old things what we were doing already, is going to impact you as an NREN. So how are you going to deal with big data? Whatever it means, of course. So everybody maybe knows the game show Jeopardy. Who knows Jeopardy? Everybody knows Jeopardy. Okay. So you always got a clue. The clue is 42. So what's the question? Yeah, what's the meaning of life, the universe, and everything? Yeah, you're right. You got points for that. Of course, everybody knows that it's from the Hitchhiker's Guide to the Galaxy. And well, in that book, Douglas Adams describes how a pandemonical tribe of people set out to the question: what is life? What's the meaning of life, the universe, and everything? So they constructed this nice computer, Deep Thought, I believe it was called, and they asked them the question. And after a long, long time, I believe it was 7.5 million years, they got back to that computer after generations and generations. They got back to the computer and they were waiting for the answer to come out. So they asked the question, Deep Thought, what is the answer to the question, what's the meaning of life, universe, and everything? Well, after long deliberation, it already took 7.5 million years to do that. The computer came up with the answer 42. Everybody knows this, of course, but 42, why is it 42? Well, then Deep Thought makes a profound statement that you really don't know the answer if you don't know what the question is. And of course he can make, and then they ask, what is the question to what's the meaning of life, universe, and everything? Well, he says, that's tricky. I have to build another computer. So, what I want to say is that even if you have a lot of tools in big data and all stuff, you can never start doing anything with these tools if you do not know the right question. So what kind of question are you asking yourself in order to use, to solve for you? You can ask the ultimate question of what's the meaning of life, universe, and everything. But that question is so broad, you will never get the right answer to that. So if you're dealing with big data, you really need to think of what kind of questions am I asking for the right answers to pop up? Because there is so much data around that statistically you can always get the right answers out of it. If you want, you can steer the answers if you like, but that's not what you want, because you want to do science, and science is a well, you want to deliver, want to get the Nobel Prize. So, but don't panic, of course. That's also from. We got a solution for that. At least IBM thought of 3 V's for big data: volume, variety, and velocity. Well, in the meantime, the 3 V's are already, there are 16 V's right now. And maybe you know this logo. There was a television series V called in the 80s, but there was a rerun. But it's about an invasion, and now we are invaded by V's and consultant companies knowing everything about big data and what you need to do to it. And probably they are rebranding their business intelligence department to do big data. I'm still going to explain a little bit about these V's, because they somehow give you some, I would say that, food ground on it, how to deal with that. First, it's about volume. Well, let me explain a bit about big data. Big data is not about volume. It's about the way you can perceive the data. So if it's for you impossible to oversee the amount of data you got, even if it's 1 megabyte or 20 petabytes, then it's big data. So if a researcher says, well, I cannot process it on my iPad, then it's big data for him. But for the guys at LHC, well, it's probably not big data. So the whole range of definitions on big data, but for me it's clearly if you cannot process it with the tools you got and don't know how to tackle that and ask the right questions, then you probably have a big data problem. Or a business analytics problem or a business intelligence problem, but it doesn't really matter. But of course, we are NRENs and we're dealing with high capacity networks, high bandwidth, so we deal with a lot of volume here. If you look at I looked at the Tarana compendium and see how, and compared to the total internet traffic last year, it was, the NRENs are producing around 0.3% of all the data in the world. 0.3%. So we got, it's ballpark. Don't point me to that figure. But it's a very small number. And if you zoom in this 0.3%, how much of that data is actually big data? I don't know. It's only internet traffic. I ignore the light paths and all this stuff. I don't know. What are the researchers doing? What are the education staff doing? They're probably doing YouTube and Facebook and nothing that comes around with big data. So is big data big data? That's the question. I don't know. It's pretty small here. I believe my problem with my kids with the 30,000 pictures is, for me, it's big data. I don't know how to process it. I keep them on a hard disk. I got them back up in the cloud. That's it. I have them ordered in directories. Yuri was mentioning in his BOF yesterday, he had similar big data problems with his photo collection. And 400,000 pictures, yeah. So, and he was thinking of how I'm going to structure that data. And now we're talking about mere individuals dealing with their big data problems, which are actually small compared to the LHC or the SKA, which is probably going to produce 1 exabyte raw data per day, which is of course incomprehensible. Of course, it's what you want to do with big data as well. It's all about gaining knowledge. It's not about gaining chaos. So somehow you need to tackle the problem with the right amount of processing power. But if the amount of data keeps on growing, there's no way you can process it. No way to do that. It's very difficult to set a hypothesis on this if you have such amount of data. What I said earlier, the statistics is so enormous, you can always get the answers you want. So how are you going to deal with that? I don't know. Bigger, bigger, biggest. Well, this is just about volume. It's from an AMC info chart. Again, the numbers doesn't mean anything. It's about the sheer growth of data, the data that's around us. But this is electronic data stored electronically. Don't forget the libraries we got with books, the VHS tapes we got with information, the audio tapes we got probably laying around. Maybe we got a whole bunch of other stuff laying around that could still add to this. But probably the digital stored data will precede all that physical stored data there. And it's going to explode and grow and grow. So how are we as NWEN going to deal with that? Are we going to let it go, just make bigger bandwidth, and let the researchers do their thing? Or how are we going to help them? Are there any tools available to do that? Are we going to take them by the hand? But we can only do that if we really understand their problems. But there are not ICT guys, there are biologists, life sciences, so do we really understand what their needs are? Another big volume picture is from Intel. It's 1 minute of data. I believe it's from last year. It's, well, if you look you can look at the numbers, but it's incomprehensible how much data is generated just by individuals alone. The number of YouTube videos, the number of logins, all this data. And this is not even research data. It's not data that comes out of the LHC. So, okay, but it's all about volume and how to deal with it. It's storing the data, it's getting to process the data and asking the right questions. Well, this is wonderful. This is actually a big compression algorithm they had at the LHC. Because it cost $10 billion US to get 1 bit of information out of that, and that is the Higgs boson exists. So, yeah, so you have a whole bunch of data running around just to prove something. Well, I exaggerate, of course. It's more subtle than this, of course, but in the end, that is perceived by the public. They spend a lot of money just to get this result. They need a lot of technology, high-end physics, a lot of innovations to do this. But it only resulted in 1 bit of information. That's wonderful, isn't it? Is that a big data? No, 1 bit is not big data, but the whole stuff behind it, they ask the right question. Does a Higgs boson exist? That's for me as a layman, of course. Yeah, it does exist. At least statistically, it exists. Another V is velocity. So I like this car, a Bugatti Veyron can go pretty fast, but data is coming in much faster if you look at the 1 minute slide previously shown. Data is generated in such an immense amount and comes from different sources. So how are you as an NWEN going to deal with that? How are you going to help the researchers to cope with this velocity of generated data? As Stephen Wolf mentioned this morning in his presentation, they get their own networks up and running. So LHC has their own network up and running to deal with the amount of data. But there are a whole bunch of researchers out there that are not LHC. It's more the small science groups. They have a lot of data as well, coming from a lot of sensors around the world. I mean, the Large Hadron Collider is a sensor to my perspective. So how are you going to deal with that? I don't know. Does anybody know how you're going to deal with velocity? Anyone? No? Well, you have to deal with it, because these people are on your network. And they have requirements on you to deal with that data, else they go somewhere else. They swipe their credit cards and go to a commercial party. They probably are too expensive, so they come back to you, complaining that they were expensive and you cannot help them. So how are you going to deal with that? Another V is variety. This is all Lay's chips. I think they are in variety, they are the best. I mean, I could look up ages for all kinds of Lay's chips variety. It's all about potato with some flavor. But data comes in with a lot of variety as well. It could be just video data, it could be audio, it could be just data from a sensor, all combined. That's all variety. It all belong to one research topic. It could be written papers produced in 1630, and how you're going to deal with that. You need to scan it, process it, structure it, add metadata to it. So how you can help the researchers again to do that. The solution is a bit easier, because every university has its library department, and a library typically knows how to deal with a large number of data, which are in their books and journals. They know how to structure it, they know how to add metadata to that. So somehow, if the librarians at the university could, say, help their researchers doing that with the collection of data, that would be a solution. And how are we as NREN going to support that group of librarians? Because nobody wants books anymore, so they get fired, the librarians, so doesn't really make sense there. Again, it's about big data. In the past, last week actually, you had a bunch of data sitting in the database, and you put queries on it, and you get answers out of that. But the amount of data is so much that you now pass data around queries. It's going just the other way around. So you got queries, and you can real time get data out of that. There are different types of people going around here. You've got the far front runners, that are the LHE types, the high physics, the astronomers. They all know what they want. They get the things they want from us because we like to provide them with the high capacity and all this stuff. But it's also about the end of the tail, for people are lagging behind. How are we going to deal with that? I will skip these slides. So how are you going to deal with the long tail of science? So it's all, I mean, we did deal with this, with the really, really big data. So they have their systems up and running. But with the small research teams that have some for them, big data problems, how are we going to deal with that? The first group, they can deal with on their own. But I think for an NREN, there is an opportunity to help the group that's tailing behind them. Because they all have similar type of problems. We can help them ask the right questions. We can then provide the tools for them and the infrastructure they need to run their analysis and get their research done. I hope that we get to that. Big tail or a big fail? I'm not sure. Thank you.
Thank you, Harold. So we have time for a few questions. I think it was very philosophical approach to this, so it was very interesting. So, some more questions? Gentlemen, you can sit down, please. There is a lot of places.
Any questions?
No questions? Okay, if there are no questions, so...
Thank you.
Thank you again. The second speaker is Bill Johnson, and I believe that he will have a totally different approach for this problem. So I introduce him a little bit. So he's working as a senior researcher for ESNet. I will repeat it again. And during his position in the ESNet went through big changes in a couple of years, and I believe that he will mention it also in his talk. Okay.
Thank you, Judy. So I have to thank Harold for generating an interesting family discussion. My son is a software developer for Industrial Light and Magic, which is the research arm for Lucasfilm. And they don't deal with post-production, but they generate the stuff that's involved in post-production. So I need to ask him what volumes of data they deal with and what they do. All right. So, excuse me. This talk consists of several things. It's a whirlwind tour through our knowledge base on tuning the network stack all the way from the optical level up to the application so that you can move petabytes a month. It's a little bit about the application experience and then a couple of other things. Why do we care about this? All of the civilian research in the U.S. is funded to first order by the Department of Energy's Office of Science and the National Science Foundation about equally. And so there are enormous collaborations involved in the Office of Science. ESNet is a facility of the Office of Science. That is, we are effectively a user facility. It is our responsibility to ensure that the communication exists to enable the collaboration so that the science mission of the office can be accomplished. Most of this is involved in, at this point in time, multi-institution worldwide collaborations, of which, of course, the LHC is typical. And data mobility is mostly what we're concerned about. I like to argue that high-energy physics is a prototype for data-intensive science. And the history of how high-energy physics has dealt with their volumes of data anticipates many other science disciplines, and we're seeing that come true now. I think you mentioned the SKA. The combined data output of the two big detectors at CERN, ATLAS and CMS, that goes to the archive centers for analysis is about 50 gigabits per second. The SKA is roughly double that. It's about 100 gigabits per second. The architecture of their internal networks is different, but it's really quite fascinating. There's a paper in last year's Tirana conference that Roisin McCool and I did on the networking problems of the SKA. It's just totally out of our scope. I mean, you're talking about millions of channels of Ethernet to move the data at the head end. So this is the kind of, the genomics community, very different architecture. You have a vast number of sequencers that feed data into a small number of repositories in quantities that are comparable. The light sources, the synchrotron accelerators that produce coherent or near coherent X-rays, they are generating terabytes of data per experiment now instead of megabytes. The reason for this is that, by and large, the data output of science follows Moore's law. And the reason for this is that most of the detectors are based in solid-state devices. And so, but the difference is, unlike your desktop computer, which sort of doubles in capacity every 18 months or doubles in data capacity, for scientific instruments, it's typically more like 10 to 20 years because of the cost of these instruments. This is roughly the history of high-energy physics experiments over the last 20-odd years, and you can see the exponential growth in data. The black line was Richard Mont and Harvey Newman's prediction of a few years ago where the LHC would be. The green line is where it's closer to where it actually is. It's not that much different, except that it's slipped out a couple of years. The blue line is the Bell 2 experiment at KEK in Japan, which of course has to be added to the LHC in terms of the total volume of data that we need to deal with in the network. And all of the Bell 2 experiment data will come from Japan to the US, and then most of it continue on to KIT in Germany. If you look at the traffic profile of our network, you see that I've overlaid our traffic profile for roughly the same period of time with the physics data volume, and it tracks essentially perfectly. And so much of the data in our traffic in our network is from the high-energy physics community, although by no means all of it. So as the instrument size and data volume have increased, of course, the methodology for analyzing the data has had to evolve. And in particular, starting with the LHC, the data model assumed from the beginning that all the data would move on the network. There would be no more handling of tapes because the logistical problems had become pretty well intractable. And similar changes are occurring in most other science disciplines. It's no longer practical to ship tapes or even RAID arrays around to transport your data. The detectors, there's lots of places you can read about the detectors. But essentially at the head end, they put out like a petabyte per second that's filtered through a series of software, hardware and software triggers to get to the 25 gigabits per second that has to be distributed around the world. And of course, the output from CMS is roughly the same. This is a schematic, which I'll come back to at the beginning, at the end of the talk. This is a network-centric view of the LHC, and there's a similar picture in our SKA paper. But this shows the data flow as it comes out of CERN, and then as it's distributed to the 11 Tier 1 centers, which are the data archives, the working data archives. And then from there, it's distributed out to some 150 odd research institutions for analysis. And so this data movement, storage, and whatnot is what drives our requirement for making sure that it's possible to move that data, which has a lot to do with both the network and the software stack. The scale of data movement is really quite amazing. I mean, there's roughly Atlas runs roughly 120 to 140,000 jobs simultaneously that are coordinated from CERN, but are distributed out to roughly 70 analysis sites over Europe, US, and Southeast Asia primarily. In 4 years, they've generated 150 petabytes of data, or rather, I should say, accumulated on their disks. And they move of the order 500 to 700 terabytes a day. And this is, to be clear, this is across seven or eight network segments. So this is the cumulative for all of the Tier 0 or Tier 1 centers in the various countries. So, the prototype aspect, our ability to move that level of data has required over the last decade or two developments at all levels, all the way from the optical signal transport through techniques of the analysis software and evolution of network architectures. And I'll touch briefly on each of these. Oops, I forgot to start my timer. Oh well. Okay, so ESNet collects on a regular basis. The Office of Science has 6 major program offices in the various disciplines of science, and once every 2.5 years, roughly, we have a requirements workshop for each of those offices. So we do requirements workshops twice a year. Those workshops involve bringing the scientific community in and the networking community, particularly the site networking community, and ESNet, and asking the science community the question, how is your process of science going to change over the next 5 years? That is, where will you be generating data? Where will that data have to move to? how will people end up using that data and so on. We never ask them what kind of bandwidth they need. That's our job to figure out. What we do is we ask them, where's your data? Where's your user community? How rapidly do you have to move the data and so on. And so anyway, in the process of doing this, we've come up with a set of issues that are essentially the same across all science disciplines, even those that don't move nearly as much data as the LHC. So therefore, identifying this common set of lessons learned is a much more useful exercise than just for the LHC itself. Okay, so we face a continuous growth of data transport. We've seen an exponential growth. The exponent is about 1.9 in ESNet as our data doubles roughly every 36 to 48 months. We're up to something like 16 petabytes a month moving through ESNet at this point. And so this is the sort of data movement at the network level that depends upon advances in the optical regime and in the switching and routing regime. So in response, ESNet, along with most other of the big R&E networks, has deployed a 100 gigabit network over the last few years. And what led to 100 gigabit? Well, advances in optical technology that go under the general rubric of coherent optics or coherent optical processing. And that's really just a term that applies to a collection of technology. Much of this is driven by, again, higher speed, the availability of higher speed processing in the DSPs that do the signal encoding and decoding, so that you can use more complex modulation, so that in per symbol transmitted, that is per optical transport unit, the smallest amount you can transport. There are techniques now that are in the 100 gig terrestrial networks that get you roughly 4 times the data carrying capability in a symbol by various encoding techniques. And so this is important because it allows our 100 gigabit payload to be carried in a standard 50 gigahertz spectrum in the ITU grid that's used for wave division multiplexing devices. This is what our optical network looks like. We have some 21,000 kilometers. There are 88 waves on this network. It's a Sienna-based system, which we split equally with Internet 2. We use 44, they use 44. We have 60 add-drop nodes that are partly regens and partly actual add-drops where we have equipment. Our layer 3 routing, our IP routing, is provided by Alcatel-Lucent 7750s, which have 100 gigabit per second client interfaces. And we have 5 of our customers now have 100 gigabit routers, so that we have 100 gigabit service to 5 of the ESNet sites, in addition to a number of network partners, primarily Internet 2 at the various exchange points. This is the layer 3 network. So one of the important considerations is how TCP behaves. There are many other protocols besides TCP which behave better in the face of network errors, but they're rarely used. TCP remains the workhorse of science. And in order for TCP to transmit to high bandwidth, long trip data, then the network must be error-free. And it must be error-free because, to quote a colleague of mine, TCP is a fragile workhorse. And it's fragile for a very good reason. The network suffered congestion collapse in the 1980s, and Van Jacobson, who was working at LVL at the time, developed the modifications to TCP that would prevent congestion collapse in the future. the way TCP was originally designed, when you got a heavily congested interface, it effectively synchronized all of the sessions, which brought the network down. And so the TCP's sensitivity to packet loss is precisely the key to triggering these congestion avoidance algorithms. What the congestion avoidance algorithms do is to reduce the bandwidth, restart TCP, and to try and find a level at which loss does not occur. There are modern TCP stacks that do better than the original Reno stack in various ways by being more aggressive in recovering from, this is from slow start to full bandwidth in an uncongested network. So it just shows you how the various stacks ramp up. This is the impact of packet loss. This graph is throughput on a 10 gigabit network versus round trip time, 90 milliseconds, roughly 9,000 kilometers. And what you have is the throughput with no packet loss, and then the throughput with a very, very small loss rate, 0.0046% loss rate. Roughly 1 in 25,000 packets are dropped. And then this is the behavior of the network stacks. And so anything out beyond about 15 milliseconds of round trip time, and you're down to 10% of the network capacity, regardless of the other traffic on the network, because bit errors and congestion drops are indistinguishable as far as TCP is concerned. They both have the same impact, that is the cause of the packet drop. If you look at if you zoom on the tail portion out there, 60, 70, 80 milliseconds, what you see is that your modern stacks do somewhat better job of providing you with resilience in the face of loss, but nothing that's going to solve the problem. So the result is that you have to run the network error-free. And the only way you can run a network, and especially a multi-domain network, as all the international networks are, is to continually monitor, test, monitor, and isolate where errors are occurring. There's lots and lots of errors, soft errors in the network that occur and don't show up in any way other than packet loss. And that packet loss frequently can only be seen at the ends. That is, there's lots of packet loss that routers don't count unless you're counting it with routers at both ends of the link and comparing the packet counts. This is an example of the kind of thing that PerfSonar will show. Somebody wasn't watching this very carefully in order for this to go on for a month. You can see that the throughput degrades gradually. This is the result of a failing optical module rather than immediately. And so that's the kind of thing that degrades performance always. So the value of PerfSonar increases dramatically the more places it's deployed, because what you need to do is, once you've found that a link is degrading, now you need to isolate the link segments, and so you really need test and monitor devices on every single segment, so you can say, aha, here's the segment that has the soft failing component, so that we can get it fixed. So there's a whole collection of system software evolution and optimizations, the TCP tuning, the modern stack that I talked about, MTU sizes, et cetera, et cetera. I'll just hit a couple of these briefly. Even if everything else is working correctly, TCP has to be tuned correctly in order to take advantage of the capacity in very long circuits. And the default buffer sizes are way too small. And even when you add in auto-tuning, which is available in most of the modern Linux kernels, it is still the case that the upper limits of auto-tuning typically are not adequate for 10 gigabit international circuits. And this is just an example. The blue line out here on the bottom shows the results of Linux auto-tuning of the TCP window size, and it really is only, somewhat effective. The green line on the top shows essentially a hand tuning, knowing what the round trip time is, what the total length of the path is, and then assigning the appropriate buffer size to TCP. In data transfer tools, you have to be very careful. Parallelism is key. That's most effective data transfer tools are, grid FTPs underlies most of what the LHC data transfers, and it uses multiple parallel sessions. Latency tolerance is critical. Some tools have latency intolerance built into them, most famously SCP. SCP only works properly in a local area network. It will not work on a long area network. And this is the Berkeley to Chicago, showing the throughput for the various tools that are available. Pittsburgh Supercomputer Center has got a patch for SCP that helps a fair bit, but you have to get 8 streams of FTP running before you come close to filling the pipe. And I pointed that out. So Caltech's FDT is another approach. It effectively is a system rather than a set of software. It uses parallel servers and parallel disks to achieve parallelism. And that group, they can fill 100 gigabit networks quite easily, as was demonstrated in the supercomputing a year and a half ago. Firewalls are your bane and enemy. And if you don't believe me, just look at Jason Zawarski's slides. Stateful firewalls, no matter how modern and how fast they are fundamentally incompatible with high throughput, long length paths. Oh, so I just want to briefly point out the obvious. If you're going to be running 150,000 jobs a day, and you're going to be moving 3/4 of a petabyte of data, obviously this has to be utterly and completely automated. There can't be any hand intervention in this. And the kind of system that Atlas has developed, I think, is sort of prototypical. There's a centralized job broker. The job broker looks for two things. It looks for available resources in a pool of some 70 sites, each one of which have a sizable cluster, and it looks for the current location of the data. And so what it does is tries to assign, the minimal effort to move data to the closest available set of computing resources to roughly optimize the overall system. And this is the kind of an automated system that is used to run this scale of this scale, as I showed earlier, of data analysis. I should point out that to build systems like that work, particularly that work at high speed over networks, requires years and years of testing. If you look, the LHC testing started of the software systems that were going to be used at the Tier 1, Tier 2 sites started some 5 years before the LHC turned on, and they were using synthetic data at a higher and higher rate, to the point where when the LHC turned on, it essentially was a smooth transition in terms of the total amount of data being handled between the testing and the output of the experiment. So this is the sort of thing that's necessary to make that kind of system successful. So the evolution of network architectures, I just want to say briefly that if you're going to transfer 50 gigabits a second, 24 hours a day, 9 months of the year, you essentially have to have dedicated infrastructure. And this is handled currently by something called the LHC OPN, the Optical Private Network, which consists of a series of dedicated 10 gigabit paths with replicas and redundancy loops between CERN and the 11 national data centers. I would point out that if this were done today in our networks that have 100 gigabit links, we would probably provide it using virtual circuits rather than physical circuits. But this network was designed and built, roughly 5 years ago, Eduardo, something like that. And so, you know, it has done the job and continues to do the job. It's also the case that this is between the tier 0 and the tier 1, between the tier 1 and the tier 2, that is the data repositories and the analysis centers. A lot of that relied on the general internet up until recently. And as the amount of unstructured traffic between the various tier 2 centers, for example, around the world increased more and more, it became clear that that had to be separated from the general purpose traffic because handling a large number of very large flows in the general purpose network doesn't work very well for either the large or the small traffic. And so the LHC-1, which is essentially a private, what it amounts to is a VPN overlay on the general purpose network, but done architected in such a way that the network operators can do traffic engineering. That is, they can select the links that are used between the various VPN clouds, which are mostly each associated with an R&E network. And that has developed over the last several years, is in widespread use today. These are the sort of extant VRF clouds that are interconnected by paths, but within that cloud and for the address space, say, of the high energy physics group, this just looks like a routed IP network. And so it's largely transparent to the end users, although not completely transparent to the sites, as it takes some configuration in order to set this up. So what we have now is we have the green cloud there is the LHC-1 environment, and is handling a larger and larger fraction of the traffic within the LHC community. And so this is a concept which is finding other uses as well. It's a concept which is useful for any sort of scientific collaboration where for some reason you want to at least somewhat isolate it from the rest of the general traffic. Science DMZ. I'm just going to touch lightly on this. It's talked about in many other places. Effectively, what it does is it uses the DMZ concept, which is a specialized zone outside of a site firewall, and says, look, we can set up a science DMZ. We can move science resources outside the firewall. We can put in an appropriate WAN-capable device, because in many cases, the LAN switches are incapable of sustaining high data rate transfers. And because these are single purpose systems and you can define per service security policy, you can deal with security in an appropriate way without going through the firewall. New network services. The point-to-point virtual circuit service is important in a small number but important number of cases, and it effectively provides virtual pipes with guarantees, that is end-to-end subcircuits within your general network that look like pseudo-wires. It's called a pseudo-wire service. I'm not going to say much about this because there's a whole talk on this topic that Chin and Vangelis and I did here at 2011, and if you're interested in the network circuit service, I suggest you look at that. So the message here is that there's a significant collection of issues all the way from the optical layer up through the application design, all of which must be addressed simultaneously in order to sustain the kind of data movement that's necessary to enable the science at the LHC. That's it.
time for a few questions. So, okay, go ahead.
Thank you for
You
your
will
talk.
get the microphone.
Thank you for your talk. It's obvious from an NREN perspective, the amount of engineering that needs to go in to support large science, big data, big science, large flows. And the NREN community has a population of engineers whose job it is to think about this. What is, in your mind, on the data generating scientists' perspective, how large does their community need to be so that they can actually have their own subset of network-focused engineers to be able to support this type of science? What is this minimal size?
This is a sociological, political question rather than a technical question.
But for certain small sets of radio astronomers,
Yeah.
this is a very critical
So,
question.
It's a good question because there's lots of small science groups out there, whether they're at the light sources doing crystallography or the genome centers, where the large-scale networking that has to support them occurs only in aggregate. And I think that this is recognized by most of the NRENs, that is, that supporting the science community, in some sense, if you look at the budgets that nation states apply to science and what they apply to networking, in some sense, there ought to be perhaps some proportionality with a scale factor in there, the scale factor being that, science is not YouTube. That is, it has different data characteristics, different imperatives, and so on. And so I think that, were I a program manager talking to Congress, that's the kind of an argument that I would make. Look, you're putting $10 billion a year into science, which cannot be accomplished unless you maintain good networks, and therefore there's a collection of NRENs, the regional optical networks and the national networks in the US, the NRENs in Europe. Those must be supported if you're going to effectively spend the science research money.
Okay, one question.
Hi, I'm Simon Leinen from Switch.
Yes.
Maybe what you just said, science is not YouTube. Science is not YouTube, and big science has these very special requirements. I tend to think that maybe it would be better to let science become more like YouTube and look at what works for the huge data transfers in the general internet and see how science can leverage these technologies like highly parallel distributed cloud systems interconnected with lots of parallel links and the data traffic distributed over lots and lots of medium rate TCP flows. I think that to me is a more promising alternative rather than this striving at all costs to keep stuff separate and have these individual very high rate transfers. To me, this is not productive in the long run. We need to get off of this scaling up mindset because it's just nonsense to try to reach whatever 100 gigabit per second single TCP throughput when there's at the endpoints. Anyway, you will have hundreds or thousands of cores processing these data. So get off of this mindset and make your traffic more like YouTube or Google's traffic. You need massive parallelism.
Okay,
and
can I respond? I've got the gist of your question. First of all, let me say that there's lots of people in the computer science community that are looking at these issues. The potential use of cloud computing for science. I believe Atlas is already using cloud computing infrastructure essentially for peaking purposes. That is before conferences and whatnot. Your example is is, you know, the science community has had this problem for years. High-def YouTube has only been enabled for the last year. We are preceding a lot of the commercial work. Will we be able to make use of content-based networking? Like I say, there's lots of people in the computer science community that are looking to answer that question, specifically charged with looking at the type of requirements and work that the science community does and seeing if this maps onto commercial services. Your example of highly parallel flows, this is somewhat unique to high energy physics. If you look at supercomputing, if you're going to talk about doing a high-resolution climate model of the atmosphere and the ocean coupled, and you have to use 3 or 4 supercomputers that are coupled together, that's not a parallel system. That's a single terabit pipe between each one of those supercomputers to make that happen. And in fact, that was the motivation for building the ESNet's 100 gigabit network, was to work towards providing the possibility of coupling the 3 major DOE supercomputer centers at Berkeley, Oak Ridge, and Chicago at Argonne. So the answer is lots of people are looking at this, and is not necessarily the case that it's an automatic panacea by any means.
Okay, thank you. So I think we have no time for this, so thank you very much. Bill, once again. The third speaker, the Stefan Pinfield, he had to return on his way to Maastricht home, but we found a way how we will chance to listen his talk, and he's connected via video conferencing system. So as I introduced him before, he's the senior lecturer of the University of Sheffield, and he worked also as a chief information officer in the University of Nottingham in the field of the schooling computing or communication, and in the librarian. So his talk opened as modus operandi for research and higher education. Okay, so please go ahead. Stefan, can you?
Okay. Good morning, everybody. Can you hear me okay, first of all?
Okay, you can go.
Yeah, can you hear me? Yeah, okay, right. Well, good morning, everyone. And apologies, first of all, for not being with you in person. As the chair just said, I had to break my journey to the Netherlands yesterday because of a family emergency. So I'm very grateful to the organisers of the conference for allowing me to deliver this presentation remotely. And apologies to you. I appreciate this is not the same experience, so apologies for that. At the moment, I can see you, I can see my presentation, but there's about a 5-second delay on when I change my slides. So I hope you'll bear with me as I try to keep everything in sync. So I'm here to represent really the team of people that were involved in the e-Infranet project. That's the European network for coordination of policies and programs on e-infrastructures. That project as a whole had a number of focuses, but one of which was on openness, and so that's what I'm here to talk about today. And the transition that we're making in this presentation compared with the previous speakers is we're moving here really from a focus on technology itself to a focus on policy and how that relates to technical development. And my slides don't seem to be moving on, so let me just try that again. Oh, there we go. Okay, so one of the two key messages of the open focus within the e-Infranet project were these. First of all, that to date, open developments have been patchy. Patchy for by a number of different developments. open. Now, I want to discuss these definitions, not really from a semantic point of view, but really to emphasize the practical implications of these definitions. And most of the definitions have come forward from particular open areas. Most of them from the open access community, but I'll quote a couple of others as well. So the first definition given here is one that I've developed over a number of years, where digital content is fully, freely, immediately and permanently available and can be viewed and reused with minimal restrictions. So the digital content within this definition may take a number of different forms. It could be textual, it could be other forms as well. Whatever form it takes, this content is fully available, that is available in its full form, its full text or whatever other form it happens to be. It's freely available, that's free at the point of access. That doesn't, of course, mean that it's cost-free in terms of its production. And it's immediately available. There are no formal embargo on its availability. And also that it's made permanently available, that is, it's available for subsequent citation or for people to reuse in various different ways. And reuse is a key issue here. The distinction I make in this definition is not only that the resource can be viewed, but also it can be reused. And so the rights restrictions on an open object should be minimized wherever possible. And that distinction between viewing and reusing is an important one in this whole discussion. It's emphasized in Suba's definition below there, where he describes open access as digital, online, free of charge, and free of most copyright distinctions. Now, also Suba famously distinguishes between different forms of openness, which he characterizes as gratis and libre. Gratis is really free to view, where the resource may be used free of charge, but libre is a greater form of openness where the resource might be reused in various different ways. In other words, rights restrictions are kept to an absolute minimum. Now, gratis and libre are not distinct categories necessarily. They are a spectrum of choices. And one of the important policy implications of this distinction being drawn here is that where policymakers want material or resources or processes to be made open, they do need to think very carefully about the kind of openness that they are recommending. So the emphasis here is on openness, not just including free to view, but also reusing as well. And this is emphasised in other definitions of openness. This one provided through the Open Educational Resources community by Wiley, who talks about the 4 Rs. He defines reuse in a specific way here, but all of these Rs, reuse, revise, remix and redistribute, talk about the reworking of materials as part of what open is all about. Now let me just illustrate why this is important, and I'm using here the example of text and data mining. Using the peer-reviewed literature as an example of material that can be mined, where the publications of the scientific community can themselves become data for analysis. So here we have a set of databases holding peer-reviewed articles, normally made available through various different agencies, such as publishers. And so we want to mine these different publications. Now, first of all, in order to mine them, you have to, in normal circumstances, copy them and bring them together into a single database. Then the resources have to be normalized in some kind of way so that they are machine parsable. Normally, when you bring them together from different sources, they will be in all sorts of different formats which have to be processed. It's only when they're normalized that analysis can take place, and then this can lead to results. And this is becoming an increasingly important area of inquiry to create new connections, to identify new research questions, and so on. So what this simple conceptual schematic illustrates is that in order for this text mining to take place, certain conditions need to be present. First of all, the content itself needs to be accessible, it needs to be available for any of this to take place. If it's hidden behind toll barriers or toll gates, this kind of activity is not possible. Then it also needs to be copyable and then configurable so that you can normalize it for analysis. So in other words, the openness that this requires is not just free to view, it has to be free to reuse as well. And that's why it's important, in order for this kind of activity, such as text mining, to take place, that the definition of openness is as broad as possible. But this schematic also illustrates an important point, which is not just to do with content, it's also to do with infrastructure. That in order for any of this to take place, there has to be a sophisticated infrastructure in place, allowing this content to be accessible, but also harvestable, to be normalized in various different ways, and then analyzed as well. And what this illustrates is the interrelatedness between different open components, that the content itself has to be open, but also there has to be a systemic openness, an openness of infrastructure, allowing any of this activity to occur. Now, bearing all of that in mind, eInfranet adopted a very broad definition of open, which included one more element, and that is open as process. And this is a part of openness which has been emphasised traditionally by the open source community. Here Weber, in his well-known book on OSS, emphasises that, as he says, the essence of open source is not the software, it's the process by which the software is created. And that idea of process or openness as activity is the final component that was brought together by the eInfranet project. So looking at open then as content, as process, as well as infrastructure. So in the report, we adopted a broad definition of open, which came from Wilbert Cran of the UK SETIS project, where he defined openness as meaning ensuring that there is little or no barrier to access for anyone who can contribute to a particular development or use its output. So that definition emphasises not just use of outputs, but also contribution as part of the openness project. So, returning then to the various different open areas that were identified by eInfranet, we can see that some of these relate primarily to content, others relate to infrastructure with some overlap between the content and infrastructure in open source, we propose, and others relate to what might be called open process. This is a high-level typology I proposed 12 or 18 months ago, which has been incorporated into the eInfranet work, and which has also emphasised open culture as underpinning all of these different developments. And there is a complex relationship between these different open developments and open culture, because open culture is required in order to generate many of these different open areas, but also we proposed as these different areas develop, they will themselves impact on culture and higher education culture. We propose as these areas are developed and are nurtured, higher education and research culture itself can become more open. Today, though, what we've seen is a set of rather uncoordinated developments, a patchwork, as it's called in the report, of open developments. Many of these have occurred at national level. They've been sponsored by national agencies such as JISC in the UK or SURF in the Netherlands. Some of them have occurred at European level, or certainly at levels above national developments as well. There have been various international consortia formed, and international foundations have also contributed to these developments. But what they have done is they focused on particular open areas. Many of them in the open content area, particularly open access, and open data more recently, OSS to a certain extent, and there's been a certain concentration on certain aspects of open infrastructure as well. But to date what we've seen is a set of patchy developments, albeit some of them significant in their own areas. And these developments have been complemented by open policy developments. Once again, some of them relating to quite local developments of particular funders, others national developments, and then there have been European and wider developments as well. Now, all of these are very significant, but once again, they are characterized by patchiness. They focus on particularly open access, most recently, or open data. There's been some policy focus on open educational resources and on some of the issues that underpin open infrastructure development, but it's still been somewhat patchy. And very few, there have been very few initiatives to bring these together. I'm aware of a very recent initiative in Poland, for example, one of the first that's happening at a national level to try and bring the different open developments together. But this is still unusual. And yet, we propose in the report, there are a number of shared benefits associated with open. And these are spelled out in detail in the report, but this is a summary of them. So some of them relate specifically to academic work, that openness creates greater visibility and impact, allowing reuse associated with academic outputs. So an example of that might be in the open access area, there's a growing body of evidence to support the idea of a citation advantage for open materials, not just open materials in terms of research outputs, formally published materials, but also there's some evidence that if data is made openly available as well, then it leads to greater citations of the work of those particular scientists. There's also an interesting argument about improved quality associated with openness. Although the evidence base for this, I think, is in need of development in some particular areas, but in the open educational resource area, for example, the work that's been done surveying those that use OER, for instance at MIT, that now makes all of its teaching materials open, the people using them, the lecturers using open educational resources, feedback that the quality of their learning objects has been significantly improved as a result of this, quite simply because their learning materials are being exposed to a larger number of people, and so therefore they are more carefully preparing them. And there's an argument that this could extend to other open areas as well. But like a lot of different arguments presented here, the evidence base between the different opens varies significantly. There is significant evidence, for example, of economic and wider societal benefit for certain forms of openness, such as open access to research outputs, but that is somewhat slimmer in other areas of openness. Nevertheless, the wider impact is becoming clearer. The societal as well as the specific academic impact is becoming clearer. And what we propose in the report is that the evidence base should be developed in various different ways. Governments are now taking account of this kind of development increasingly in the whole area of transparency and accountability, and that's what's driving much of this development. And so it needs emphasising that the academic community can, or at least has the potential to take a part in this wider societal development by forwarding the mission of universities in terms of the impact on society. And that, I think, is something that university policymakers need to emphasise in terms of their alignment with this kind of agenda. There are, however, a number of significant challenges in this whole area of openness. And I'll mention a couple of these. They're listed in the report, which you can look at. The first I've already referred to is about levels of openness and about the policy implications of different levels of openness, which need to be clear in policy development. There are whole areas around disciplinary differences and the extent to which disciplinary publication cultures, data management cultures and so on differ, and the extent to which that impacts on the levels of openness that are appropriate. One key area that is focused on in the e-infranet work is this whole area of evaluation and reward incentives, because reward incentives at the moment largely focus on published outputs, and so there is little incentive in many countries at least, and as far as many research funders are concerned, to encourage, for instance, sharing of research data or participation in infrastructure development or software development. And so what we propose in the report is that policymakers, particularly funders, have to look more carefully at trying to encourage a wider set of incentives to be developed in the academic community, not just focused on publication, in order to promote greater openness. I've also referred to cultures, but one of the things we were conscious of is the whole area of skills development in this area, particularly associated with developments such as data sharing. Processing of data is a good example where skills development in the academic community needs to be promoted in order for that to take place. And finally, this whole area of defining the limits of open. Nobody, or certainly nobody associated with the intranet, is saying that everything should be shared, but there should be a clear notion of where the boundaries are so that policy development can go forward with, for instance, a clear understanding of where the limits of openness are. So just for example, in the area of published outputs, the business models and structures that have been proposed for open access largely relates to the royalty-free, peer-reviewed literature. They don't relate to literature where royalties are involved in terms of author income, because the business models for open access are problematical in that area. So that's a good example of where a limit, a natural limit, seems to exist in terms of openness, and that needs to be reflected in policy. So finally then, just to summarise the recommendations and actions put forward by e-infranet, that open should be, where possible, the default modus operandi for research and higher education. That, in other words, there should be a shift. At the moment, openness is often a special initiative within the academic community. We are proposing that over time it should become the default modus operandi for the academic community. There could be exceptions to that, of course, but it should be the default way in which people operate. And that requires open content, open process, and open infrastructure to be working together. And that means the adoption of a generic open policy framework that can inform the different developments of different open areas. So we're not saying that all of this needs to be a monolithic policy whole. Different open activities can proceed in different ways, but they need to be held together by a general policy framework and with a shared mission. So the action points we're proposing are, in order for this to happen, is that where possible, funders should recommend that open development methodology takes place for publicly funded projects, and that research outputs and other outputs are made open wherever possible. To underpin this, there needs to be a review of evaluation and reward frameworks, as I've mentioned, and also greater advice on copyright licensing and IPR issues to enable open to take place. There needs to be significant skills development in these various different areas, both around policies and cultures, but also technical developments as well, of course. And interoperability of systems, services and content needs to be promoted as part of funded programs. And we also propose that where possible, R&D needs to be continued in all of these areas to improve good practice, to continue to enhance the technical infrastructure, and to promote an understanding of the evidence base. Now, all of this was a joint team effort. I'd like to acknowledge our funders, the European Union, and also various different colleagues who are listed here who took part in the e-Infranet project work and wrote the final report. So I'll finish there, and I'm very happy to try and address any questions. Thank you very much.
Okay. Thank you, Stefan, for your talk. So probably you understand and discovered that this session was not only about the big data, but also about the openness. Sorry for that. So we can open the floor for question. So, okay, if there are no questions, so we will thank Stefan again. And before you will leave...
Thank you very much.
Okay, thank you. Before